we are going to look at is how to draw circuit diagram for the given output. Okay, so when we start drawing something like an expression in Boolean, okay, always keep in mind these basic things I'm going to teach you. Okay, we are going to do the reverse process of finding out the output. That's what we consider by drawing the circuit. Because in the last video we talked about the question gave us a circuit and you had to find the output. Now they are giving you an output. For that you are going to draw a circuit. So exactly the reverse, that's what we are going to do. Okay, so we have the solution, we have to find the subgates, and we have to go to the signals. That's it. Very simple. Okay, so if you have something like Q is equals to A dot B, you clearly know we are using only an AND gate. Okay, there are two signals. Okay, and this dot represents they are passed through a AND gate. Okay, AND gate. So A, B, and they are passed through an AND gate. Okay, so this is what we understand by reverse engineering, or anything, call it anything you want, but this is what we are doing. If you have something like Q is equals to A plus B, well, that means we are using an OR gate. There are two signals A and B. We are using an OR gate. So we have A and B, and they are passing through an OR gate. Okay, they are passing through an OR gate. Okay, and if you have something like Q is equals to A bar, okay, well then that means it is passing through a NOT gate. So we have the signal A, this bar represents that the signal A is going through a NOT gate. Okay, it is going through a NOT gate. These are the basic gates. Okay, I can go on with an NAND gate, NOR gate, XOR and XNOR gate, but you know the idea, right? So if you have Q is equals to A dot B whole thing bar, well, that means they are passing through a NAND gate. Yeah, there are two signals A and B. If there is a dot and they are covered with a whole thing bar, well, that means the signals are passing through a NAND gate. Okay, they are passing through a NAND gate. Similarly, if you have Q is equals to A plus B whole thing bar, well, that means they are passing through a NOR gate. Okay, so you have A and B, the signals A and B. Since you have a plus and that is covered with a whole thing bar, you can clearly see they are going through a NOR gate. Okay, and we have XOR, which is pretty simple. Instead of having dot or plus, here we have a plus covered with a circle. That's it. That's what we call a XOR gate. Sorry, an XOR gate. So we are passing through that. We have A, we have B. The output will be A XOR B. And if you put a bar here, well then you just have to put a circle here. That's all. So this is the basic idea. Okay, and now we are going to find these A and B terms. Okay, the A term can be anything. It may be say like x plus y. Okay, it can be like x plus y. Well, if you have x plus y, you have to understand at the end of the circuit. Okay, this specific input. Okay, this specific input is then passed through an AND gate with B. Okay, I don't know whether I made sense. Well, let's do a practice question. This is the cheat sheet. Okay, this is the cheat sheet that you want. Okay, keep this in mind. We can do any questions. Okay, so let's say this is the first question. Let's say we have Q is equals to A plus B into A plus C. Okay, so what we are going to do is we are going to reverse engineer this thing. Okay, I know there are three inputs A, B, and C. Okay, but what you have to first do is, okay, look at this. Okay, look at this. You can clearly see two terms. We have a term here, we have a term here. Okay, we have a term here, we have a term here. And here you can clearly see there is a dot, which means A plus B and A plus C are passed through an AND gate. Okay, A plus B and A plus C are passed through an AND gate. But then we can't stop here because we know A plus B is not a single signal. It is composed of two signals and that contains A and B, and we have a positive symbol, a plus symbol, which means A and B are passed through an OR gate. At the same time, A and C are passed through an OR gate. So what this means is, okay, we have three signals. So obviously we have to draw the input lines. Okay, we have to draw the input lines. Let's draw that first. So input lines. Okay, now we know, first of all, A and B are passed through a AND gate. Okay, so let's have A. Okay, let's have A and let's have B and let's send them through an OR gate. Why? There is a plus symbol. Okay, and they are behaving as a single signal in this specific expression. So let's pass them through an OR gate. Okay, so that's it. We have passed them through an OR gate. Perfect. So here we have A, here we have B, which creates us A plus B. Similarly, there is A plus C. So let's also have A plus C for our answer. So here we have A, here we have C, and here we have the OR gate. Okay, here we have the OR gate. So this is A and this is C. The output will give us A plus C. Okay. Finally, A plus B and A plus C are sent through an AND gate. They are sent through an AND gate. So let's send them through an AND gate. Okay. So we are sending them through an AND gate. That's it. That's it. Here we have A plus B. Okay. Here we have A plus C. Okay. So the output will be A plus B into A plus C. Okay. A plus B into A plus C. So this is how you have to draw. Okay. So we have the solution with us. We have to find the subcase. We need an AND gate. Okay. And then we need two OR gates. Okay. We need two OR gates. And then you just have to pass through the signals according to the question that is given to us or solution that is given to us. Okay. So let's try another one. Something like Q is equals to A dot B whole thing bar plus C bar whole thing bar. Okay, so first of all, what does this say? Well, there is a whole thing bar here, which means you can think of it as two ways. Okay, a signal is coming and that is passed through a NOT gate. Okay, or it is passed through a NAND gate, NOR gate, or a NAND gate, or an XNOR gate. Okay, and it can be or it can be an XNOR gate. Either four gates are possible for this given output. But what you have to look for is here what symbol do we have? Okay, inside the brackets, obviously inside the parenthesis, over the parenthesis we have the bar. Okay, which means these four are the options. Okay, if we didn't have anything, just a single term like X bar or A, B, sorry, we can't say even A, B bar, just X bar or Y bar, something like that, then it's not gate. Okay, you can directly go for the NOT gate. But if you have a plus symbol like this between two terms, this is a single term, this is a single term. Okay, so since you have plus here, okay, we can definitely say it's an XOR gate. Sorry, it's an OR gate. Okay, if you had instead of plus, if you had a dot, well, that means it's a NAND gate. And if you had an XOR symbol, well, then it will be XNOR gate. Why? It is covered with a whole thing bar. Okay, it is covered with an whole thing bar. Please keep them in mind because this is very important when you're drawing circuits. Okay, you should be able to visualize what's going on. Okay, so at the end, we need a NOR gate. Okay, but then here we have C bar and here we have A dot B whole thing bar. Again, the same story. Here you have whole thing bar and here we have a dot, which means it is A and B are passed through a NAND gate. You got it right. And then here just C and a bar. Okay, well then we just need a NOT gate. That's it. Okay, very straightforward. So let's do that. So first of all, we need the signal lines for A, B, and C. So let's draw that first. Okay, so this is A, this is B, and this is C. Okay, A and B are passing through a NAND gate first. So let's do that. So they are passing through a NAND gate. So let's take A and B and pass them through a NAND gate like we do. And that is done. Okay, now we have to pass C through a NOT gate. So let's pass C through a NOT gate. Perfect. Now we have to pass these two signals, like this is A, this is B. The signal that we get here is A dot B whole thing bar. Illaya? Similarly, here we have C, this is C bar. Now we have to send them through a NOR gate. So let's send them through a NOR gate and we will get the final answer. Okay, so we'll send them through a NOR gate. And that's it. So here you have A dot B whole thing bar. Here you have C bar. So the final output will be A dot B whole thing bar plus C bar whole thing bar. See, you got the answer. Okay, so it's again and again, it's the same thing. Find the subgates first. Okay, what is the final gate? What is the next step? What is the like that? Go again and again. That's it. So let's do another practice question in this state. Okay, let's say Q is given as A XOR B whole thing bar plus A dot B whole thing bar whole thing bar. Well, here you can see we have whole thing bar. So we have five choices, right? No, we have four choices. Not, NAND, NOR, XNOR. Since you have a plus here, finally these two signals that we have are passed through a NOR gate. So we need a NOR gate at the end. Okay. Then we have two subgates. Here we have the whole thing bar, which means again four suspects. But then since you have XOR here, it is an XNOR gate. So we have XNOR gate. And then here, A dot B whole thing bar, which means we have a good, you answered correctly, NAND gate. Okay, so that's it. Okay, we just have to pass them. That's it. So let's draw the inputs lines A and B. Okay, let's draw the input lines A and B. So A and B. A and B are passing through an XNOR gate first. So A is here, B is here. Let's pass them through an XNOR gate. Okay, that is done. Then we have to pass them through an AND gate. So let's do that too. Now we are here. So let's pass them through an AND gate. Perfect. So here we have A, here we have B. So the output will be A XOR B whole thing bar. And here we have A, here we have B. So the output will be A dot B whole thing bar. What do we need next? Well, we need a NOR gate. This one is done, this one is done. So we need a NOR gate. So let's send them through a NOR gate. Okay, so that's it. NOR gate. So this is the OR gate. If you put a circle in front, it will be a NOR gate. So here we have A XOR B whole thing bar. You can say A XOR B, and this is A and B. Okay, so the output will be A XOR B whole thing bar plus A dot B whole thing bar whole thing bar. That's it. Okay, that's all you have to keep in mind. Okay, so now we have done two sections, right? We are passing through two specific layers of gate. This is the final layer of gate. Okay, this is the final layer of gate, and this is the first layer of gate, which means there are only two layers, right? There are only two layers. That's what we have. What if we had three layers? Okay, something like Z is equals to A plus B plus C plus A dot B whole thing bar plus A plus B whole thing bar. Okay, and then plus instead of plus, let's say we have dot C dot B whole thing bar whole thing bar. What if we have something like this? Let's put a bar here also. Okay, what can we do here? Okay, this is a good question, right? Because it looks complex, very complex. You can't just do the question. Yeah, you can't just do the question. How are we going to do this? Well, let's remove this parenthesis and let's put, you know, braces. That's there. Okay, how are we going to do this? It's the same thing. Okay, reverse engineering, right? Reverse engineering. Let's use yellow color first. So here you have whole thing bar. Okay, here you have whole thing bar, which means there are only four suspects, not NOR, NAND, XNOR. Okay, well, since you have a plus here, okay, just because I'm circling doesn't mean it's XNOR. Since you have a plus here, these two signals, okay, these two signals are passed through a NOR gate. So at the end, we have a NOR gate. Okay. Then what do we have? Well, let's talk about this specific signal. There is also a whole thing bar. Okay, which means there are four suspects. But since you have a plus here, these two signals, yeah, these two signals are passed through another NOR gate. Okay, and let's talk about here. Here you can see these two signals are passed through a NAND gate. Why? There is a dot here, there is a whole thing bar here. So there is a NAND gate also in the game. Okay, and let's talk about NOR gate again. So here you have A plus B plus C, which means they are passed through an OR gate. Okay, they are passed through an OR gate. What about this guy? Well, A and B are passed through a NAND gate. Why? There is whole thing bar and there is this specific dot. So there is an AND gate. Okay. And what about this guy? In NAND gate, what about this guy? Well, we have A plus D whole thing bar, which means A and D are passing through. Yes, you got it. NOR gate, right? Because there is a whole thing bar and there is a plus symbol. So there is a NOR gate again. What about this guy? We have C dot D holding bar. Well, that is a NAND gate. That's it. Okay, this is NAND gate, right? Because A dot D whole thing bar, which means that's an NAND gate. So how many gates do we need? Well, 7. That's it. Okay, and what you have to do is you just have to pass through all the signals. So first of all, let's draw the signal input lines A, B, C, D. Right? Here we have 4 signals. Okay, so let me know in the comments how many rows will be there in the truth table, how many combinations will we get. Okay, so let me know in the comments so that we can learn together. Right. So first of all, what are we going to do? We are sending through OR gate A, B, and C. So we have A here, we have A here, we have B here, and then we have C here. A, B, and C are passing through an OR gate. Okay, they are passing through an OR gate. Perfect. So if this is A, this is B, and this is C, not if, they are A, B, C. So it will be A plus B plus C whole thing. Okay, whole thing inside the parenthesis. And then we have A dot B whole thing bar. A dot B whole thing bar. So which means they are passing through a NAND gate. Good. We are passing them through a NAND gate. A and B. A, so they are passing through a NAND gate. Let's draw the NAND gate. So yeah, A, B, and this is A dot B whole thing bar. Okay. Before we go to the second layer, we'll just finish all the first layer things. Here we have A plus D whole thing bar, which means they are passing through NOR gate. We have already drawn the mind map. So we need A here. Okay, so let's pass through A here. So A is coming, and then we have D. So let's pass through D here. So they are passed through a NOR gate. A, they are passed through a NOR gate. A and D are passed through a NOR gate. So A plus B whole thing bar. Okay. Then we have C dot D whole thing bar, which means C and D are passing through a NAND gate. Very good. So that's it. Let's pass them through a NAND gate. So we have AND here, then we have NAND here. So C and D, wow, two C's passing through a NAND gate. Okay, if that is a simple idea like that. If you know, let me know in the comments what that means. Okay, what happens if you pass the same signal inside a NAND gate? Okay, that's it. So we have C and D. Okay, and they are passing through a NAND gate. So the output will be C dot D whole thing bar. Now we can go to the second layer of gates. So we have NOR gate. Why? These two are passing through a plus and a whole thing bar, which means they can only go through a NOR gate. That's the only combination possible. Or they can pass through a NOR gate and then a NOT gate, but they can just use NOR gate, right? Because they didn't say we have to use basic gates. Yeah, I'm writing the question, so use any gate. So the output will be A plus B plus C plus A dot B whole thing bar whole thing bar. Okay, and similarly they are passing through a NAND gate, so let's draw that also. Okay, they are passing through a NAND gate. Oh, I forgot to write here. A plus B plus C. Here we have A dot B whole thing bar, and this one is A plus B whole thing bar, and this is C dot B whole thing bar. Okay, so they are passing through a NAND gate. Okay, so they are passing through a NAND gate. That's it. So what will be the output? So that will be A plus B whole thing bar dot C dot D whole thing bar whole thing bar. That's it. Okay, and then these two are finally meeting with a NOR gate, the final and the third layer of gates, the special NOR gate. Okay, so it passes them through the NOR gate. What will be the output? We'll have the output Z. Okay, I don't think I can write it here, so I'll just put Z here. Okay, so here we have the first, the final layer, third and the final layer. Here we have the second and the intermediate layer. Okay, and this one is the first and the starting layer. Okay, so if you can break down the expression, B expression, into different layers, well, you're set. Yeah, you're set. That's all you have to know. So you can use a mind map. Okay, you can use a mind map, and yeah, that's it. So write down some random expressions. Here, write down some random expressions and draw them by using, the logic gates. Okay, this is actually related to, finding out how an algebraic expression works. So if you have something like 4 plus 3 into 2 um, divided by, still saying divided, just subtract. Yeah, subtract 4 plus 3. Okay, so if you have something like this, okay, according to the PEMDAS, okay, according to the PEMDAS, you will simplify this question. Okay, you will simplify this question. So first of all, you have to do what's inside the parenthesis. Okay, some people do first of all 4. Okay, and 3 into 2 is equals to 6 minus 4 plus 3, because that's the one in the leftmost corner. At the same time, it's the parenthesis. Then you will do the 4 plus 3 because that's inside the parenthesis. So 4 plus 6 minus 7. Then you will do 4 plus 6, which is equals to 10. Then you will subtract the minus 7, you will get 3. Okay, you can either do like this, or since these two have the same precedence, okay, you can directly find the parallel execution. Okay, you can just skip this step. Okay, you can just skip this step and directly go here, and then you can skip this step because addition and subtraction have the same precedence, so the order doesn't matter. So you can go to this step. Okay, so how did you come to this? After this, okay, obviously you started at this point, but then we learned to do in this way, right? And when it comes to simplifying algebraic fractions and all, we just blast through it, right? Integration and differentiation, we just blast through it. We somehow know how to factorize and simplify everything. What did we learn there? Patterns. That's it. They are patterns. Okay. Your brain will ring an alarm when it sees a pattern that it already knows. Okay. And that's what I want you to do in logic gates also. If you see an expression, your brain should be able to break that down into different layers and how many gates are required and what gates are required. Everything should be in your fingertips. That thoroughness I require from you. Okay, it's better if you have that. If you can do that, that's really cool. So yeah, draw as many expressions. Write as many expressions as possible and draw them in your free time. Okay, do them daily. You don't have to spend 4 hours or 5 hours daily. Just do 10 minutes daily. Yeah, for the next month maybe. That's enough. The 300 minutes that you put in these 30 days will make a huge difference in your future. Trust me, it will. So yeah, stay tuned. We are going to learn about Boolean expressions. Okay, how we can simplify these expressions. Yeah, we have to know that also. So we are going to learn about Boolean algebra. Okay, it's a different world. Okay, it's very interesting. So stay tuned. Don't miss any video.
Thanks for watching the 6th video in our Logic Gates series.
If you found this deep dive into drawing circuits from Boolean expressions using reverse engineering, layers, and mind maps helpful, don't forget to like, share, and subscribe for more lessons. Hit the bell icon to stay updated with our latest lessons. Check out the full playlist to master logic gates. Follow us on Instagram. I will see you in the next video. Until then, keep learning and stay curious. Bye bye.